My name is Dominique Hager, and the topic of today's presentation is simulation modeling in big data and Hadoop environments. So my focus actually over the next 35 to 45 minutes is on introducing basically the modeling techniques that we utilize to basically conduct studies that revolve around big data in Hadoop. I'll show you several different simulation models that are being used in different phases of these big data and Hadoop projects. We're pretty much covering everything from the cradle to the grave. So we are involved with due diligence studies. We're conducting proof of concepts. We're involved in the design phase, the deployment phase, and then when the systems are actually in operation, we use, again, simulation modeling techniques to optimize the environment, to conduct capacity evaluation studies, scalability studies, but also availability, reliability, maintainability projects. We're also branching out into the security aspects of these big data and Hadoop environments. And then we also basically are involved in studies where customers incorporate the traditional RDBMS systems that they have deployed into big data in Hadoop environment. Let me say this first. Big data and Hadoop, these two terms are not synonymous. The term big data basically refers to the vast amount of heterogeneous data that's generated at a very rapid pace, and that actually basically yields the traditional data analysis tools that we're using for RDBMS systems as being useless. So we're dealing with structured, semi-structured, and unstructured data here. The real value actually of big data is in the insights it generates when analyzed. So it's really about extracting value out of a massive data pool. So it's about the discovered patterns, it's about the derived meaning, the indicators for decisions, and ultimately actually the goal is to respond to the ever-changing business world in a timely fashion and with greater intelligence. When it comes to big data analytics, we basically refer to a set of advanced technologies, and these technologies are designed to efficiently operate on very large amounts of heterogeneous data. So we're talking petabytes of data there. So the technologies are based on rather sophisticated quantitative methods such as artificial intelligence, we have machine learning, we have neural networks, but also robotics and computational mathematics. And all these techniques are actually used to aid in exploring the data to discover these unknown interrelationships and patterns. Hadoop, on the other side, actually, the traditional Hadoop is described as a Java-based distributed computing framework, and that framework is designed to support applications that are implemented via MapReduce programming model. So traditional Hadoop, we basically define as HDFS, the Hadoop Distributed File System, and MapReduce applications. MapReduce is nothing but divide and conquer. It's not a new technique at all. It's actually derived from functional languages such as Lisp or ML, the meta language, and it basically operates in a master-slave setup. The design strategy is different, from what traditional RDBMS systems offer, in that we move the actual computation to the data, versus with a SAN that powers an RDBMS system, we actually move the data to the computation. This slide number 2, basically outlines the different phases that we go through for any big data and or Hadoop project. I'll get to the goals and objectives. It's very important, it's actually paramount that any big data and or Hadoop project starts off as a business mandate. And I'm going to give you several examples throughout the presentation on that. The first thing we do basically is we're setting up hardware profiles. The hardware profiles basically depict the upper bound on the capacity potential of your hardware. But that capacity potential can only be closely approached due to protocol overhead. And then we actually, if we have a test environment in place, we're collecting application and OS data. We utilize, it depends on the project, either sophisticated agents that we develop basically in-house to collect the data, or we just use Linux commands that basically are coming with the operating system. We can make the call actually that any big data and or Hadoop project is powered by the Linux operating system. So that really narrows down the focus on one OS. So these agents only have to be basically designed, developed, maintained for one particular operating system. After we establish the hardware profiles and the application and OS traces are taken, we're doing the first phase of data post-processing. So that's where we try to recognize patterns, we do statistical analysis. In that phase, we're already heavily relying on machine learning. We're using artificial neural networks. Self-organizing maps are very popular in that particular phase of the project to post-process and already derive value basically out of the application and OS traces. Other techniques used are convex folds, which is a simpler approach than a self-organizing map, but still gets the job done. And then based on the results of the post-processing phase, we establish the workflow profiles. The workflow profiles, they basically depict the dynamics of the application infrastructure. And it also basically, the profiles quantify how much of the hardware capacity is actually being used. So again, what we learned out of the hardware profiles is already being used, when we establish the workflow profiles to get a feel for how much of the hardware capacity is actually being utilized by the production environment or test environment. And after that, actually, we're conducting performance optimization studies, and I'll show you several simulation models that actually fit into phase 4 of this project plan. Depending on the project, we're also working a CSA study. That CSA term stands for Cohesive Systems Assurance, and basically incorporates reliability, availability, maintainability, and security. So it all basically gets fused into one common study where we analyze and quantify the interrelationships among, the different entities. After we have an optimized environment, depending on the study, we may conduct a capacity study, which is basically a headroom analysis, or we conduct a scalability study where, again, modeling based, we actually increase the workload as well as we basically introduce additional components into the big data and or Hadoop infrastructure. We're using, depending on the project we're working on, we're using different modeling techniques and different tools. Let me say this actually, the question we're trying to answer basically drives the complexity of the models. We're also trying to, basically design and develop the simplest model possible that allows us to answer, the question. So again, depending on the project we work on, we may use a deterministic stochastic Petri network. We may use some artificial neural network. We may even do some model predictive control or some fuzzy logic actually to answer the question that's actually on the table. And I will show you several models that basically fit into these, different categories, so you really get a feel for how we actually operate. So again, big data is really basically the business of just operating in a very, very, very large volume, environment of heterogeneous data. We really have to deal with unstructured, semi-structured, as well as, structured data. So we have to incorporate basically some of the legacy data warehousing environments into our big data solution, and Hadoop may or may not actually be part of, your big data solution. One trend actually that's obviously visible out in the wild is that a lot of these companies who are interested in big data, they move from batch to real-time processing. And the statement can really be made that real-time supports predictive analytics. So that's definitely an area where a lot of companies are heading to. It's important, as I already said, it's very important that you start off with a business mandate. So if you want to basically reduce the time to answer from X hours down to Y minutes, then you really have, a business need to at least evaluate the big data and or Hadoop solution. So at that point, actually, if you're able to, let's say you have a forecasting package, if you can actually reduce the time to answer from hours to minutes, at that point the application becomes an interactive business tool that's really changing the way your company is conducting business. Another, area where we're really involved with is the POCs, so the proof of concept. So some of my customers, they basically build, let's say, a 16-node Hadoop environment, HDFS, and they have a MapReduce application running. And then the question to be answered actually is, what happens, to the performance behavior if we increase the data set, that we're using right now, let's say 1,000 or 5,000 fold. So how many nodes and how do these nodes, have to be set up from a tuning perspective so that we still basically are within the SLA? And again, these are projects, that require basically a modeling-based solution, because you cannot build these environments and run actual sensitivity studies. Another thing we're doing basically is if you have a production environment, let's say in the cloud, and your company, is leasing, let's say, 1,000 nodes, if we conduct a performance optimization study, you may be able to reduce the number of nodes, let's say, from 1,000 down to 650. And just the reduction in nodes basically reflects a huge cost saving for the company. And again, these performance optimization studies that we're actually conducting are basically modeling based. We also do quite a bit of trend analysis. So you may actually have a big data solution in place right now. Let's say from a real-time perspective, you're using the Apache Storm solution, and not to overrun basically your Storm environment, you may have a message broker like Kafka in place. So the spouts are actually basically getting the input from Kafka, and then the bolts basically, conduct the logic in your real-time application, and then for, let's say, visualization or additional post-processing purposes, you're actually dumping some of the data into, let's say, a Cassandra data store. So again, we're taking basically performance data off the Kafka clusters, Storm clusters, the Cassandra clusters, and we're trying to basically establish a relationship among the workloads on the different cluster systems via the models, so we can do a trend analysis, so we can tell customers, you know, down the road you need more nodes in your Cassandra cluster, or you need fewer loads in your Cassandra cluster, which again, if you lease basically the environment in a, you know, in a cloud setup, results into huge cost savings for the companies. So we always basically stress the point that if your company is interested in branching into big data or Hadoop, to do a proof of concept, because at the end of the day, actually, the solution has to work with your people, your data, your algorithms, and your infrastructure. And just because it looks good on paper does not mean you can actually pull it off in your, you know, in your environment. So again, the proof of concept is paramount. It's important that you actually build at least a prototype at a small scale, and then we use the models basically to extrapolate, you know, increase the workload, tune and set up the nodes that were still within the SLA. This is basically a partial view of the big data and Hadoop ecosystem. So down here, that's where you may have some of the legacy RDBMS systems, and we aid customers in, you know, incorporating RDBMS into a big data environment. Depending on the project you're working on, you may or may not use Hadoop. Okay, as I said, you may be focused more on a real-time processing environment where you could use, you know, a component like Storm, or you have Kafka. I was talking about Kafka, basically, you know, serving as the buffer before you know, utilize the Storm infrastructure. And then as a data store, you have several options, obviously, you know, in big data. You could choose Cassandra. Most customers, they operate in a Hadoop, you know, MapReduce HDFS environment. They normally use an HBase, you know, as the data store, or you can use a Hive or a Pig, which is basically a higher level of abstraction when it comes to MapReduce. You can write your application in Hive or Pig, and then they basically compile into MapReduce code, so you don't really have to, you know, write MapReduce code yourself. So again, you know, these are considered Hadoop components, whereas a lot of the projects out there these days, they're really focused on real-time processing. And then we also have the machine learning libraries like a Mahout, a Spark, a Hadoop, or a Hema. And depending on, you know, what you're trying to accomplish with your project, you know, we basically aid you in making the decision to go either with a Mahout or a Spark, which are kind of at the two extremes of the scale-up. Mahout just recently made good strides, though, so they're going more into in-memory computing, so they're really trying to, you know, catch up with some of the other machine learning libraries available for big data. So what I want to do now actually is really show you models that we use in our environment, you know, to aid customers with these big data projects. So as I said, the first thing we do basically is we establish these hardware profiles. Now we're using very sophisticated models basically to quantify the capacity potential of your hardware. So we're building models basically at the CPU abstraction layer, the memory abstraction layer, the I/O abstraction layer. I mean, normally big data clusters, they operate in local disks. So normally there's no SAN per se involved with the big data solution. And the other big thing obviously is the interconnect. I mean, we're dealing with very, very large clusters. So we're building very sophisticated models actually that allow us to quantify, the capacity as well as the performance behavior of, let's say, your, GigE, 10 GigE, or InfiniBand interconnect setup. What I'm showing you here actually is a CPU memory module for the Intel Sandy Bridge architecture. This is a very popular setup actually for big data. So this could be, it's an E5, what I'm showing you here, an E5 2680. This could be a Dell, an R720. So you see basically this system has two CPUs, and then we have each CPU basically has 12 DIMMs, and we have 4 memory connectors basically into the CPU on each side. So CPU 0, CPU 1, they both have 4 connectors basically into the DIMMs. And without populating any memory at this point, you can see the model basically tells us that per memory channel basically the bandwidth is 12.5 gigabytes per second. And this is important to big data in Hadoop because a lot of these applications are actually, either focusing on in-memory computing or are rather memory and CPU intensive. So you really want to be able to run at the capacity potential of, your setup. So now what we can do actually is we can populate memory into, these different systems. I'm just going to use dual rank 32 gig memory modules at this point. Dual rank just means that the block or area of memory consists of 2 64-bit wide data areas. So I'm just going to put some memory in this system, and we'll analyze basically the capacity potential of the hardware while we actually configure memory. So this CPU now is configured with 128 gigabyte of memory, and you see we're still basically with this setup running at the full bandwidth that we can actually get out of the hardware. The problem starts when I actually add additional memory into the equation. You see now the configured memory speed actually is starting to drop because we're having 2 DIMMs actually served by this memory channel. So our memory bandwidth drops from 12.5 gigabytes per second to 10.4 gigabytes per second. So the old saying actually that adding memory into a server system never hurts performance is just not true. Okay. So we use models like this basically in the design phase or the analysis phase to either optimize the setup for your particular big data and or Hadoop environment, or to understand, the capacity potential of your hardware, if the system is already in production. And again, we're using models like this for anything, from basically the BIOS, the block IO layer in Linux. We have models basically where we look at the hardware components and then we map basically the Linux abstraction layers, onto the hardware to really understand basically the performance potential of the environment. From a CPU perspective, because we're dealing with Linux, we also have models basically that map into the hardware where we basically simulate the red-black tree that's being used in Linux to dispatch threats, okay? Or we simulate the radix tree that's being used for basically the page cache in Linux, so that we understand from an OS perspective, how much of that available hardware capacity can we just actually utilize, from a Linux perspective. And then with the workflow profiles that we have, that we establish in phase 3, we can basically replay the load that your particular application puts on the environment and run this through the OS abstraction layer and map it onto, the hardware models that we're building here to basically, compile the entire story of your workload on Linux with your hardware infrastructure. So from an optimization perspective, actually, I'll show you a model here that focuses on Hadoop, the MapReduce aspects. So again, these are basically the hardware, attributes that we get out of the hardware profiles, and we're masking actually some of the OS related aspects as well in this model, like the I/O scheduler. I mean, in 2.6 and 3.x, you still have 3 different I/O schedulers at your disposal from a Linux perspective. So in these models, actually, we can mimic either the completely fair queuing, the deadline, or the no-op scheduler. We can also basically play around with the read-ahead size, which is paramount, actually. This is the Linux read-ahead size. And the mapping from a MapReduce application onto Linux, in most scenarios, it requires basically adjusting some of these, Linux-specific parameters to really get up to the capacity potential of the hardware. And then down here, basically, we have Hadoop tuning and setup parameters. So this is basically what you can, tweak and tune from a Hadoop perspective. We know what the default values are, and in these models, actually, while we're doing the analysis, we can basically set them up the way to optimize the runtime behavior application and allow you, again, to really get up to the capacity potential of your hardware. And then what we do basically in this model is we mathematically abstract the 5 faces of the map side of the MapReduce application. So we're talking about the read, the map, the collect, the spill, and the merge phase that basically make up the map part of the MapReduce application. And then we do the same thing for the reduce tasks. And the reduce tasks, basically, they go through a 4-phase process where first we shovel, then we merge, then we reduce, and then we write. So the read, basically, in the map phase comes out of HDFS. The merge phase, basically, if it happens, or the spill phase, we only want to spill once in MapReduce, happens in the local file system. So this is probably ext4 in your environment. And then in the reduce phase, actually, when we shovel, we basically move the data from the map nodes to the reduce nodes. So that's where we actually have the interconnect heavily being used. And then in the write phase of the reduce task, that's when we write the results basically back into HDFS. So this is just a little summary of how a MapReduce application works. And all these different phases, these 9 phases, 9 potential phases, doesn't mean you're going to go through all 9, are mathematically abstracted in this model. So you can see basically the different phases. We can zoom in, drill in, and evaluate and quantify the performance behavior in each phase of the map in the reduced task. And at the end down here, we're basically plotting the MapReduce application execution time. So you can see for a 256 node cluster with this particular application and the tuning that's actually applied right now, it's taken around 9,000, let's say 200, seconds to process this application. So what we're doing now actually is we're going in and we're making some tuning changes, okay? So what we do first is we actually increase, in the model basically, we're increasing the HDFS block size, okay, from the default of 64 meg to 256. And then we also increase the Java heap space from the default 200 meg up to 1,000, okay? We're working with the map and the reduce tasks. This obviously has to fit into the hardware setup of your environment. So we set that to 16. And then we also do some tuning actually when it comes to the spill behavior of your MapReduce application. So I'm going to basically tweak and tune some of these parameters a little bit. And just because we tune it a little bit does not mean there's only a little impact. So these parameters really have a profound impact on the behavior of your environment. So let's see how the behavior is now after we tune some of these parameters. Okay, so we're just basically going through the same phases of our MapReduce application, and then we'll want to basically quantify again the impact on the runtime behavior. And you see we were up on 9,200 without the tuning, and now our 256 node cluster actually is processing everything in 1,300 seconds. So again, we didn't have to build a 256 node cluster to quantify the performance behavior, okay, which is mathematically abstracted all this, and we're using basically these models to optimize, to do performance optimization, which in this scenario also could actually, basically result into being able to reduce the number of cluster nodes. So if your SLA is around, let's say, 3,000, seconds, you could potentially run with only 128 nodes, and if you basically lease these nodes in the cloud, you could significantly reduce the cost factor, that's associated basically with your Hadoop MapReduce environment. All right, the next thing I want to show you actually is an actual forecasting exercise where we use artificial neural networks. So these are basically performance checkpoints that we got off a cluster system. So we see on the timeline, this is basically the timeline. We can see how many MapReduce tasks were active. We see the memory behavior of the system. We see the network behavior, the interconnect behavior of the system. And we also see basically the I/O behavior of this particular application on the timeline while our MapReduce application actually is running. So what we want to do now is we want to do some capacity evaluation and kind of determine if we increase the number of MapReduce tasks, so if we have a higher concurrency level, is the hardware actually capable of absorbing the additional load, and where's the break-even point? So I'm just going to run this artificial neural network real quick, and we will analyze the results. While this is running, let me say something about the error behavior. I get that question a lot. I mean, with an artificial neural network, you have basically a training phase, and then you basically, analyze and quantify an error, whatever it is. It could be a mean squared error, it could be a root mean squared error, it could be a mean absolute error. And I always get the question, so when it comes to, modeling, what is a good error rate? And there's no absolute criteria for a good value for a root mean squared error or a mean absolute error. It really depends on the units in which the variable is measured and on the degree of forecasting accuracy which is measured in these units that is sought after by your application. So it makes no sense to say if the model is good or bad just because the root mean squared error is less or greater than X, unless, and that's the kicker, unless you are referring to a specific degree of accuracy that's relevant to your forecasting application. Okay, so that's just, a couple of minutes on, error behavior with machine learning based models. So now we see basically from a concurrency level at the CPU perspective, when we actually have these MapReduce tasks running, we see basically the relationship with our I/O subsystem. Okay, so we see basically the more threads we have running, the higher the demand basically in our, I/O subsystem, especially actually in the spill and the merge phase of our MapReduce application. So if we, again, increase the concurrency level, okay, we want to see if our I/O subsystem, local I/O subsystem is actually capable of absorbing the impact. And you can see the answer is we do not have that much room left, okay, from a CPU to I/O perspective to really increase the concurrency at the CPU level, because we would basically saturate and overrun our I/O subsystem at this point. You see basically the knee of the curve is somewhere around 14 or 15 concurrent tasks. If you actually increase beyond that, your response time curve, which is not shown here, this is the throughput curve, would increase exponentially, and you would really suffer actually from an aggregate application, response time behavior if you go beyond, 14 or 15 concurrent map-reduced tasks here. So again, this model is based on machine learning. It's an artificial neural network that's being used. And the other one I want to show you actually is what the trend analysis is all about. I talked about the data flow, Kafka into Storm into Cassandra. So on the timeline, basically, we collected performance data on an environment that consists of 2 Kafka clusters, 2 Storm clusters, and then there's 2 Storm clusters that feed data into a Cassandra cluster. And Kafka, we actually collected the messages per second. In Storm, we basically work on tuples. So we basically, we got aggregate tuples per second for the Storm clusters. And then in Cassandra, basically, we're up to the transactions per second. So on the timeline here, these are the values, messages per second, tuples per second, and transactions per second that we basically collected. And we want to do a trend analysis. Let's assume this cluster actually runs in a cloud environment, and the customer wants to know, based on a trend analysis, do I need more Cassandra nodes or do I need fewer Cassandra nodes? Can I reduce? Can I take some of the Cassandra nodes out of the cluster and save some money there? So let's run this simulation model. It's going to take a little while, so I'm just going to let this one run basically, and we'll revisit it, and I'm going to show you a couple other models, and then we'll actually come back to this one. What I want to say actually, this model is based on inductive learning, so this is basically a learning by example based technique. So let me try to close this window. I'm actually on a laptop here that's not that powerful, so it may take me a little while to be able to close this window. But anyhow, you see that some of the results are already coming in, but I'm probably overloading my CPU subsystem here a little bit. So let's look at this model. This basically is an HDFS simulator. We get a lot of questions from customers like, okay, we have HDFS in production. We have built-in redundancy in HDFS. So each data block basically is by default is being replicated 3 times in your cluster. So let's say they have n nodes and they utilize a replication factor of 3, which again is the default. Their question is, how many of these nodes can we actually lose? You have an outage, nodes go down, they get fenced. How many nodes do we still have to assure data integrity? Okay. And this is what this model actually is all about. And I want to show you results, so I'm not going to run a huge cluster. I have an 8-node cluster where I use a replication factor of 3, which is, again, it's the default for HDFS. And I'm using 100 blocks, basically, to populate first my cluster. And then I start out of the simulation model, I start to fail nodes, okay? And I want to answer the question here is, how many of these 8 nodes do I have to have up and running while still basically having HDFS in a state where everything is runnable, okay? So let's run the simulation, and I'm going to pipe into more here. So the first phase basically is we're just setting up the HDFS cluster with all the data nodes, and then we start populating populating basically these blocks from block number 0 all the way to block number 100, and you replicate. You can see block 0 is being replicated on 0, 2, and 6. Okay, 1 is on 1, 7, and 3. So we just step basically through, this process of getting, all the nodes into the cluster. And then after this is done, okay, each node obviously has a block layout that shows us the different, blocks that we're holding in, the different nodes. And then I'm going to start basically failing nodes, all right? So I'm starting to fence nodes. And while this looks basically like it's happening sequentially, I'm really basically simulating an outage where multiple nodes are just going down. And again, I want to go down to basically the node count that shows me how many of these nodes are required to sustain data integrity. So we're failing node 5, we're failing node 7, we're failing node 4, and at that point the simulator basically tells me I have to stop. In order to sustain data integrity, I have to have, in this scenario, node 2, node 0, node 1, node 3, and node 6 up and running. So in other words, if one of these 5 nodes goes down, we cannot actually have HDFS still up and running in this particular environment. The other model I want to show you basically revolves around Cassandra. Cassandra basically is a peer-to-peer setup. It's a data store. Very, 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 very good when it comes to performance. Extremely low read and write latency. And it uses basically what's called a gossip protocol to introduce nodes into the cluster. What that basically means is we're dealing with a ring topology in Cassandra. And when you actually have a node joining the ring, then that node only communicates gossips with a subset of the nodes. And then these nodes basically gossip to a subset of the nodes. And then it basically just cascades from there, okay? So gossip is basically the protocol being used in Cassandra, and Cassandra is actually written in a programming language called Scala, okay? So what we did actually is, because Cassandra is written in Scala, so what we did is we also implemented our simulator in Scala. So the first benchmark I want to show you actually is we want to quantify how many nodes each node is basically communicating with via the gossip protocol while we establish a Cassandra cluster of 500 nodes. And we also want to understand the latency behavior that's actually, required to set up that 500 node Cassandra cluster. So we're simulating basically node membership as well as to transmit some system control states so that we actually have the Cassandra cluster in a runnable, from a transient into a steady state, behavior. That's basically what we're simulating here. So we have, it's written in Scala. We use basically our application, our simulator called Gossip. We're basically simulating 500 nodes. They are set up in a ring topology. They utilize the Gossip protocol, and this is the per node latency to basically simulate membership and to transfer some system control state information to the other nodes. This number is not made up. This number we get out of the hardware profiles, as well as basically the profiles we establish for the interconnect. So this is interconnect related. So now let's just simulate, the setup of 500 Cassandra nodes, and you see per node we have an average of 33 communication tasks, and on average actually the latency that is affiliated with the different communication tasks necessary to set up the cluster is 61.05 milliseconds. Okay. Another question that we want to answer is, in Cassandra, if a client requests data, let's say we do a read, the data in Cassandra is replicated like it is in HDFS, all right? So on a read operation, it is necessary to assure that the read data is not stale, okay? The data exists on n nodes in your Cassandra cluster. So the data, because it's replicated on n nodes, we have to use what's in Cassandra called the digest, which is a hash of the data, okay? And we use that hash basically to assure that the read data on these different Cassandra nodes is synced up. If it's not, we have to do a read repair, okay? So on a read, the digest is used first, and then if we actually are sure that we're not working on stale data, the actual data is being transferred to the client. All right, so let's simulate this. Let's say we have a 600 node Cassandra cluster still set up in a ring topology, but now actually we are not interested in just the communication behavior. We're interested in basically the application behavior. So we change basically the function from gossip communication to application calculation. And let's say this particular operation has a latency per node, latency behavior of 11.2 milliseconds. Okay, dealing with the digests, okay, so that we're assuring that we're not working on stale data. So now I'm running basically the simulation, and you see now actually, in order for all this to happen, each node communicates, while we're simulating this workload with 75 other nodes in your ring, and the per node aggregate latency behavior for each of these Hadoop cluster nodes is 840 milliseconds. All right, so now we have the output back actually from our trend analysis. So you can see basically this is based on inductive learning. This is basically the curve we're getting back from our model. And you see the trend still goes up, but then starts to flatten out. So based on this curve, actually, we can determine how many Cassandra cluster nodes do we have to still stay within the SLA. All right. And the last model to basically wrap up the presentation that I want to show you is we also operate quite frequently at a data center level, okay, where we're dealing with different racks that comprise basically these big data in Hadoop environments. And if you have concurrency, synchronization, and randomness, deterministic stochastic Petri networks are very, very good to conduct an actual analysis. So this Petri network basically shows two racks, rack 1 and rack 4, which basically host big data real-time applications, and then rack 2 and rack 3, they basically have some batch processing that revolves. This could technically be Hadoop, okay, because we have tasks that finish, versus with real-time, you're basically just feeding data into your cluster, so it's perpetual. Excuse me. So let's run the simulation, and you see we're just basically putting a load actually on the interconnect, as well as the different racks, and on a per rack basis we can establish performance as well as capacity baselines. The way Petri networks work actually is they're layered. So this shows you basically the rack level, and then we layer down to really basically the node level, and then on each node actually we have Petri networks in place that allows us to quantify the performance behavior, let's say at the bio level, the block IO level of Linux, where this high level workload up here is broken down to the node level, and we we can actually utilize Petri networks to fine-tune the Linux operating system. You know, as an example, we can, in rack 1, basically, we can switch the IO scheduler from CFQ to, let's say, NOAP, or from CFQ to deadline, and quantify the performance behavior at the node level, and then basically, you know, populate everything up until we reach this high level again, where we're looking at the different racks. So this is kind of how it works, and thank you very much for your time. Appreciate it.